Well, next question. Now we can do a little bit of calculus, calculate the derivative of a plane curve. How about the area of a curve defined parametrically? Right? We know, area, as long as the function is non-negative, would be from x being a to x being b of the function dx. Right? Well, in terms of t, that'll become, this is t being a to t being b, y of tx prime of t. You'll see that here in the next one. So let's go through and do it for the area under this parametric curve. And let's go ahead and find a few. Let's do some table of values here for just a sec on this one. Let's throw some points in for t being greater than or equal to 0. Actually, let me do square root of 2, square root of 3 would be a good one. Square root of 4, which is 2. Those are all some good points on this. 0 squared, 1 squared, square root of 2 squared, and so on. 4t squared minus t to the 4th, look at 0. 3. Plugging that into 4t squared minus t to the 4th. And so, and you could also, just to review, you could eliminate your parameter as well to help you kind of draw this thing. If x equals t squared, t is the square root of x, and then y is 4t squared minus t to the 4th. So y equals 4, t is root x to the 4th. And so y is 4x minus x squared. In other words, negative x squared plus 4x. And so you've got your zeros. If you actually factored a negative x out, you'd have zeros at x being 0, x being 4. And we already know we have that point. We have those points 0, 0, 4, 0, right? And we've also got 1, 3, we've got 2, 4, we've got 3, 3, and so on. And this is our parametric curve. And of course it keeps going as well. But we're just finding the area under the curve and the x-axis, right? So we're just trying to find this area right there. So the area bounded by the curve and the x-axis would be that'd be from an x value of 0 to an x value of 4. Right? This is x being 0, x being 4 of y dx. So what's our y? Well, our y here is 4t squared minus t to the 4th. So there's our y. Our dx. What's our dx? Well, let me go to the side here. We have x is t squared. So I know dx dt is 2t. In other words, dx is 2t dt. That's my dx. 2t dt. Now, what about the x being 0 to the x being 4? Well, if x is 0 and x is 4, well, we know x is t squared. So if x is 0, t would have to be 0. If x is 4, t be plus or minus 2, but we know t's got to be greater than or equal to 0, so we're just going to pick the 2 here. Notice the t was greater than or equal to 0. That's given. 0 above. So this is from t being 0. When x is 0, t is 0. When x is 4, t must be 2. You could have actually seen that on the table. when x is 4, t is 2. When x is 0, t is 0, right? So we could have seen it right there too with that given table. But let's go ahead and run this now. Let me distribute that. So I got t being 0 to 4. I've got 8t to the third minus 2t to the, oops, that's not 6, that's 5th, dt. And so we got 8t to the 4 over 4 minus 2t to the 6 over 6 from t being 0 to t being, oops, that's not a 4, that's a t being 2. 2. So we got 2t to the 4th minus t to the 6 over 3 from 0 to 2. So we got 2 times 16, I got 32 minus 64 over 3. So we got 96 over 3 minus 64 over 3. 32 over 3. So that area between that parametric curve and the x-axis there is 32 over 3. And note, by the way, for this one, it does work. You could have used that rectangular equation from x being 0 to 4 of negative x squared plus 4x dx and just ran that, and yeah, it would be the same thing. So you could check this normally. Let me go ahead just to kind of get a feel or draw this ellipse here. Let me go ahead and eliminate the parameter. I know sine squared t plus cosine squared t is 1. See how the sine of t, if I solve this for sine of t, I'd have y over 3. If I solve the cosine, I'd have x over 2, I'm sorry. So I have x squared over 4 plus y squared over 9 equals 1. And so what I have is, remember, a is bigger than b, so that's my a squared right there, because a is always bigger than b for ellipses here. So this is an ellipse with a major axis. Since that a squared is underneath the y, this major axis is vertical. It's centered at hk at 0, 0. And you're centered here at 0, 0. Your a squared is 9, so the vertex is a distance a squared equals 9, so a of 3. 1, 2, 3 to your first vertex. 1, 2, 3 down, so it's elongated vertically. A is 3, so your vertices are 0 plus minus 3. Your co-vertices come from the b value. That's b distance away. So b squared is 4. So I got plus or minus 2, 0. I got to go a distance of 2 to the left of the center, distance of 2 to the right of the center. I could also, so here's kind of your graph. Step 2. If you wanted, you could plug in some values as well. You're going from 0 up to 2 pi. You're throwing in the x is 2 cosine of 0, which I know is 1. So my x value is 2. My y is 3 sine. Plugging in 0 in for t. I know the sine of 0 is 0. I get 0. And I do that for pi halves. I'd get that 0, 3. And I'd get the rest of these points here, which happen to be right at my vertices and co-vertices. So it's going from 2, 0 up to 0, 3. And then to negative 2, 0. Oh, it was so good until the end. And I was so proud of that ellipse. What a great shape I had. Try that again. Oh, that is pretty good. I'm proud of that. Anyways, got our parametric curve. It's trying to have us find the area of this, right? So what I'm going to do is I'm actually going to take a fourth of it, and I'm going to find that area and then just multiply by 4, right? And so this step 4 here, this area would be 4 times that. So I'm going from x being 0 over to 2 of y dx, right? And so we've got 4. If x is 0, then my t is pi halves. If x is 2, then my t would be 0. Of my y is 3 sine of t, 3 sine of t, and then dx dt. Let me go to the side here. I have x equals 2 cosine of t, dx dt would be 2 negative sine t. So dx is negative 2 sine t dt. There's my dx. Negative 2 sine t dt. So 4 times 3 times negative 2, I got negative 24 going from a t being pi halves to 0 of sine squared t dt. And so I'm going to have to use my power reducing formula on this. If you want to look back at your power reducing formulas, sine squared of t is a half of 1 minus cosine of t, 2t. Whoops. So we got t being pi halves to 0. And so we've got negative 12, 1 minus cosine of 2t dt. So that would be negative 12 integral 1 minus 12 times negative cosine. So that's a plus 12 cosine of 2t dt. I split that up. So I've got negative 12t plus 12. I'll go ahead and write this. Let me write this a little bigger. Because I got to use u sub here. So I need a 2, I need a 1/2. Six, that's the integral of cosine u du. Now I run the integral of the cosine, which is sine of u. And there's our integral. We're going from t being pi halves to t being 0. So I've got that's 2 times 0 minus halves 6 sine 2 times pi halves. So I got 0 plus 0 minus, that's a negative 6 pi plus 6 sine of pi. I know the sine of pi is 0, so that's 0. So this just ends up negative 6 pi. So this just ends up being 6 pi. That's our area. area is 6 pi. Of course, it's whatever our units are squared. Well, let's get into arc length. This is the development. You're welcome to read through that if you'd like to. I'm going to jump to this arc length formula here. So we've got here's our arc length formula written two ways there. And let's go ahead and use that right here. Find the arc length of the curve on that given interval. So the first thing you want to do, take your x and your y. Let's find dx, dt. Let's find our dy. Now that we have dx, dt, dy, dt, let's throw that into our arc length. The arc length is from A to B, square root of dx, dt squared plus dy, dt squared dt. And so we've got from, this is A to B, it's on the interval from A to B. So a t value of -1 to a t value of 3. Square root, our dx dt is 3, so that's being squared. Our dy dt is -2, that's being squared. So we're going from -1 to 3. 9 plus 4, I got the square root of 13. And now I'll run that integral. So I got square root of 13t, -1 to 3. So we got square root of 13 times 3 minus square root of 13 times -1, or 3 square root of 13 plus square root of 13, or 4 square root of 13. So our arc length is 4 root 13, or if you want to punch it in, that's that right there, 14.422. This is a good problem if you want to pause the video and find the arc length from A to B. So find dx dt, find dy dt, and then go ahead and plug it into your arc length formula. And that, I wrote that wrong. That's 6t squared right there. So your dx dt is 12t, your dy dt is 6t squared. So this becomes from t being 1 to t being 4 over the interval. Dx dt is our 12t, dy dt is 6t squared, dt. So we got 144 t squared plus 36 t to the 4 from 1 to 4. And so I would take out a 36t squared. So you're left with 4 plus t squared. Square root of a times square root of b is square root of ab. So I could take the square root of 36t squared, which is 6t. And I got the square root of t squared plus 4 tt from 1 to 4. And then we can go ahead and let u be t squared, whoops, t squared plus 4, 2t dt. I'll give it a 2 and offset it here. And so let me take the 6 out front. 6 times a half, I got 3. And then I got the 2t. And you see there's my du. Alright, there's my du. So square root of u du. And so we got 3. That'd be u to the 3/2 all over 3/2, so times 2/3. Our u here is t squared plus 4. This is from t being 1 to 4. 3 times 2/3, 3 cancels, so we got 2 t squared plus 4 to the 3/2, 1 to 4. I got 2, I got 4 squared plus 4 as minus 2, 1 squared plus 4, 3/2. What is that? 2, I got 20 to the 3/2 minus 2, 5 to the 3/2. So my arc length, if I take a 2 out, or this is a pretty cool one. You've got x being r cosine t. So you're using the definition of the arc length in parametric form to find the length of the circle of radius r, right? Well, what's the length of the circle of radius r? That's what we're going to find, right? So what's this arc length? Well, dx dt. R is a constant, right? So the r stays there. I got r times negative sine t. So dx dt is negative r sine t. Again, remember r is a constant here. Circle of radius r. So we got r cosine t. And then let's throw it in from A to B. So we're going from 0 to 2 pi. Dx dt is negative r sine t, that's being squared. Dy dt is r cosine t, that's being squared dt. And so this ends up being from 0 to 2 pi. I've got r squared sine squared t plus r squared cosine squared t dt. So I've got square root of r squared sine squared plus cosine squared. Well, we know that's 1. So we've just got square root of r squared, t being 0 to 2 pi. So we've got r dt from 0 to 2 pi. And so we've got RT, t being 0 to 2 pi. So we've got r times 2 pi, r times 2 pi minus r times 0. So we got 2 pi r. That's the arc length of a circle. In other words, that's our circumference, right? We just developed, using the arc length formula, the circumference of a circle. But we're going to also do area of a surface of revolution for parameterized curves. So go ahead and use that. It's similarly stated above. Use either of those. We're going to do it for revolving it. Let's see, I'm going to do this in about the x-axis. And so we're going to use this first one here. I'm going to revolve it about the x-axis. So we've got, well, first of all, we've got x being cosine of t. We're going to need dx dt and dy dt. And so the, back up here again, I'm using the area of a surface of revolution. So capital S here, area of a surface of revolution, going from t being 0 to 2 pi. Oops. And we got 2 pi, and we've got the y. Let me write the formula first. This is dx dt squared plus dy dt squared dt. Okay. And so we've got from 0, 2 pi, and we're going to throw in our y. Well, our y is 1 plus sine of t. And then we got dx dt being squared, dy dt being squared. Well, we know sine squared t plus cosine squared t is 1. So we got square root of 1 there. dt, I could put that 2 pi out front, taking the integral of 1 plus the sine of t. And so we've got 2 pi, integral of 1 is t, integral of sine is minus cosine t, going from 0 to 2 pi. And so we've got 2 pi, we got 2 pi minus cosine, 2 pi minus 0 minus cosine of 0. And so we got 2 pi times 2 pi minus cosine 2 pi is 1, minus 0 minus cosine of 0 is 1. And so we've got negative 1 plus 1, those are gone, so 2 pi times 2 pi. So we've got the area of the surface of revolution being 4. Oops, let me make that a little better. Revolution, 4 pi squared. And this is kind of a picture of that to the left here as best I can. This, again, another good you try it problem if you want to pause it, but you have x, you're going to have to find dx d theta in this case. Instead of t, we have theta. That's the only difference here. Find dy d theta, and then we'll go ahead and we'll throw it into the area of a surface of revolution. This is going about the x-axis. We're going to use that same theta being a to theta being b, 2 pi y dx d theta squared plus dy d theta squared d theta. Well, I filled out my dx d theta, my dy d theta. Make sure you're using the chain rule on that dx d theta there. And we're going from theta being 0 on the interval up to a theta being pi halves. We got 2 pi y is cosine of theta. And then we've got square root of dx d theta, so squared, plus dy d theta squared. I'm going to put that 2 pi right there, the cosine theta. And then we got negative 2 squared, I got 4, I got sine squared, cosine squared, plus sine squared. I'm going to factor out a sine squared. So we got 4 cosine squared theta plus 1. I know the square root of sine squared And then I'm going to let my u be 4 cosine squared theta plus 1. So that would be 8 cosine theta times negative sine theta d theta. So du is negative 8 cosine sine d theta. So I need a negative 8. Let me give it a negative 8. Let me offset it. And here's my du part. So we just got the square root of u du. So we've got u to the 3/2, all over 3/2, so times 2/3, and our u here is 4 cosine squared theta plus 1. And then this will be from 0 to pi/2. And 2 over 4 is a half, so I got negative pi/6. Let me do it like this. So I got 4 cosine squared theta plus 1. 3/2. pi/2. I'm going to put that constant out front there. So I got cosine of theta squared plus 1, 3/2 minus 4 cosine of 0 squared plus 1, 3/2. I got cosine pi/2 is 0, so I got 4 times 0 plus 1, all the 3/2. Cosine of 0 is 1, so I got 4 times 1 squared. Three-halves. So I got negative pi/6. I got, that'd be 1 to the 3/2, which is 1. That'd be 5 to the 3/2. So 1 minus 5 to the 3/2. Let me change that, take a negative out. So I got pi/6. Change those signs. There it is. Or come over here. 5 to the 3/2 is the same as 5 root 5. Or you can punch that in. And that is 5.3304. And there's the area of the surface. Thanks so much for watching. See you next time.